Okay, question 26 on the math subject GRE practice test. This is a really cool question. Props to the test makers here. We have this function f of x, which is defined kind of strangely. It's whichever is greater out of these two expressions for x values from -2 to 2. And what we're supposed to do is evaluate the definite integral from -2 to 2 of that function. So when you see this notation right here, you might be thinking, all right, figure out the antiderivative, plug in the values, and I'm done. Right? It's the evaluation theorem. It's your very standard Calc 2 question. Well, that's true, but kind of doing the problem that way is going to be pretty hard for a few reasons, really. One reason is it's not obvious which of these is greater for a given value of x, so we'll have to spend a little bit of time just to define this function f of x, just to take care of this max part of this function. The second reason is when you're figuring out antiderivatives, this one is super easy. This one's actually pretty hard, right? We'll have to use a trig sub in here. It'll take a little while. I mean, I'm going to do it because I think it's good practice for you to have, but my point is just this is a challenging integral. As is often the case on this test, if you can be a little bit clever with what's going on, you can save yourself a lot of time. And clever in this context means think about the more geometric interpretation of this. Rather than using the evaluation theorem, antiderivative, plug in endpoint, subtract, that kind of stuff, think about this as just representing the area underneath the curve from -2 to 2. Let me sketch you a picture. If I graph y equals x plus 2, that's really easy, right? It's y equals mx plus b. The b is a 2, the m is a 1. It's just a line whose y-intercept is at 2 and whose slope is 1. Sure didn't plan that out very well. It's a line that looks something like this. Sure, good enough. But what about the graph of the square root of 4 minus x squared? That the y-coordinate is the square root of 4 minus x squared. And while you might not recognize this graph, if you square both sides, you get y squared equals 4 minus x squared. If you add x squared to both sides, you get x squared plus y squared is equal to 4. And maybe written in this notation, you'd recognize that this is just a circle. More specifically, it's a circle centered at 0, 0, whose radius is equal to 2. How do I know that? Well, because I teach math for a living, but also because the standard form of the equation of a circle looks like this, where x1, y1 are the coordinates of the center, and r is the radius. So what I have here is what I have here with zeros plugged in for x1 and y1 and 2 plugged in for r. So you're like, so I have a circle? Well, almost. When I square both sides of the equation, I lose some information. Really what I have here is the top half of a circle. And that's because if you think about solving this equation for y, when I take the square root of both sides to kind of return up here, I got to put in a plus or minus in front of my square root symbol. The fact that I kept the positive solution gives me the top half of the circle. Had I kept the negative solution, it would have given me the bottom half of the circle. Note that if y were negative this thing, when I square both sides, I get to this exact same point. But I don't have negative this thing. I don't have the bottom half of the circle. I have the top half. Anyways, if you can get this far, you can answer this question super easy. This function is defined to be the max of these two things. So the higher of these two things from -2 to 0 is the graph in blue. And then the higher of these two things from 0 to 2 is the graph in red. So to evaluate the definite integral from -2 to 2 of this function, I need to know how much area is over here, but then also how much area is under here. Well, good news, that's a fairly easy geometric problem. What I have here is a quarter of a circle, right? A circle with radius 2. So you know that the area of a circle is pi r squared. So since r is 2, the area of this entire circle would be 4 pi. But I only have a quarter of the circle, so this area right here is just equal to pi. What about this area over here? Well, I think it's easiest to break this up into a triangle and a rectangle. I guess a triangle and a square, if you're really nitpicky. Although if I'm really nitpicky, I'm saying that a square is really just a special rectangle, so I wasn't wrong. Whatever. This area down here is 2 by 2, so it's got area of 4. This triangle up here has a base of 2 and a height of 2. 1/2 the base times the height tells me that this area is 2. The total shaded in area is pi plus 2 plus 4. In other words, pi plus 6. C is the correct answer. Kind of cool, right? I suspect that this is how the test makers wanted you to solve this problem, and I think it's the best way to solve this problem. But it's not the only way to solve this problem. You could also do it more algebraically. And while doing so wouldn't be smart on this specific problem, maybe it would teach techniques that you'd need for a different problem. So I'm going to go ahead and do that too. So okay, I've copied the problem down here. I'm going to suppose that I have no idea what these graphs look like, and I'm going to try to solve this thing completely algebraically. Well, the challenge here is since my function is defined as the max of these two expressions, if I'm going to use the evaluation theorem, take an antiderivative and plug in points, I need to know which of these two is greater and where they're greater. One way you can do that is you can take the two expressions and set them equal to each other. The reason that works is these two expressions are continuous on this domain. So in order for one to kind of overtake the other one and become bigger than it, they must be tied for an instance. This is going to find the instances in which they're tied. To solve this equation, what I'm going to do is first square both sides of the equation to get rid of this square root symbol. Be careful here. In this specific case, it's not going to matter, but generally when you square both sides of an equation, you lose information, right? I'm going to solve this equation down here now. Maybe I solve and find some value of x that makes this side equal to 4 and this side equal to 4. So I'm feeling really good about that value of x as a solution. But maybe that value of x makes this side 2 and this side -2, right? 2 is not equal to -2, so that value of x should not be a solution. But when I squared both sides, 2 squared turned into 4, and -2 squared turned into 4. So I got an apparent solution down here that wasn't really a solution. The point that I'm trying to make is it's fine to square both sides of the equation, but when you do so, make sure you check your answers at the end. It won't matter here, but it's a good habit. Solving this equation, I'd expand this side and get x squared plus 4x plus 4 is equal to 4 minus x squared. And now if I add x squared to both sides and subtract 4, kind of combine like terms, I'd get what? 2x squared plus 4x equals 0. Easy enough to solve. Maybe factor out a 2x, and you get 2x times x plus 2 equals 0. So 2x equals 0, in which case x equals 0, or x plus 2 equals 0, in which case x equals -2. What I just figured out are the x values for which these two things have the same height. But what I really want to know are the intervals on which this one is bigger and the intervals on which this one is bigger. So if we consider our domain from -2 to +2, we know the only places they have the same height are at -2 here and at 0 here. So I've taken this original domain from -2 to 2, and I've kind of broken up into two different regions, region 1 and region 2. What I can just do is test the two expressions in region 1 and then test the two expressions in region 2 to figure out which one is bigger in each region. To test the two expressions in region 1, I can pick any number I want in region 1, anything that's greater than -2 and less than 0. I'll pick -1 just because that usually makes the math work out pretty nicely, but you don't have to pick -1. This is sort of an arbitrary choice. If I plug -1 into this expression, what -1 squared is 1, 4 minus 1 is 3, so I get the square root of 3. If I plug -1 into this expression, -1 plus 2 is 1. Root 3 is bigger than 1, either because I just know that, or because 1 is the square root of 1, and the square root of 3 is bigger than the square root of 1. What I'm saying is that on this interval from -2 to 0, f of x is equal to the square root of 4 minus x squared, because f of x is always the greater of these two things. At this point, you'd probably just assume that on this region, the other function is going to be greater, because otherwise they wouldn't have defined the function this way. They would have just said f of x equals the square root of 4 minus x squared. But I'll go through the steps anyways. Pick any number you want on this region. I don't know, test x equals 1. Over here, 1 squared is 1, 4 minus 1 is 3, so I get the square root of 3 again. But over here, 1 plus 2 is 3, and 3 is bigger than the square root of 3. Again, either because I just know that or because 3 is the square root of 9, and the square root of 9 is bigger than the square root of 3. So over here, f of x is equal to x plus 2. So really, this function that's defined to be the maximum of these two expressions, I can think about as just a piecewise function that takes on the value the square root of 4 minus x squared if x is between -2 and 0, and takes on the value of x plus 2 if x is between 0 and +2. Note that I gave 0 to this function. I could have given it to this function. It doesn't matter. They have the same height at 0. Thinking about f of x in this piecewise fashion gives me an easier way to evaluate the integral from -2 to 2 of this function f of x. Now, all I have to do is evaluate the integral from -2 to 0 of the square root of 4 minus x squared, and then add to that the integral from 0 to 2 of the expression x plus 2. Cool, this is something I can do. If I can figure out these two antiderivatives, I plug in values and I'm done. Good news and bad news. This one's really easy, right? So easy that maybe I'll squeeze it in up here so I have room for later. The definite integral from 0 to 2 of x plus 2, figure out the antiderivative, which is 1/2 x squared plus 2x plus c. I can ignore the plus c and evaluate this thing from 0 to 2. Plugging in 2's, I get half of 4 plus 4, in other words 2 plus 4, which is 6. Plugging in zeros, I get 0 plus 0, which is 0. 6 minus 0 is 6. Oh yeah, that 6 feels familiar, right? That's just this 6 right here, right? The area underneath this curve, y equals x plus 2, from 0 to 2. What about this one? Oh, well, I may be missing something, but I think the easiest way to evaluate this is with a trig substitution. Let's see, I think I'll choose x equals 2 sine of theta. I think you could choose 2 sine of theta or 2 cosine of theta, but maybe this will keep things positive. Let's see, if x is 2 sine of theta, then dx is 2 cosine of theta. So the indefinite integral, so I don't have to mess with the endpoints, of the square root of 4 minus x squared can be rewritten as the indefinite integral of the square root of 4 minus, 2 sine of theta squared. In other words, 4 sine squared theta. And then instead of dx, I got 2 cosine of theta. But a nice thing happens here. I could factor out a 4, which turns into a 2 when I pull it out in front of the square root sign. And then that 2 and this 2 turns into this 4. Underneath the radical, I got 1 minus sine squared. But maybe you remember that 1 minus sine squared is just cosine squared, so I got the square root of cosine squared. And that's what the absolute value of cosine. Hopefully that won't end up being a problem later on, that absolute value. I got cosine of theta from here and cosine of theta from here, so I got cosine squared theta. I guess I should be tracking my d thetas, so maybe I'll toss that over here. Good enough. All right, great, you changed the integral. That's wonderful. What's the antiderivative of cosine squared? Well, bad news. I don't know the antiderivative of cosine squared, but I do know there's this thing called the double angle formula. And one version, I don't even know where, of the cosine double angle formula tells me that cosine of 2x is equal to 2 cosine squared minus 1. So if I solve this equation for cosine squared, add 1 to both sides, divide by 2, I get that cosine squared x is equal to 1 plus cosine of 2x divided by 2. So instead of writing cosine squared theta here, I'm going to write 1 plus cosine of 2 theta divided by 2. This is better because this 1/2 I can just pull it out in front and make it 2 times the integral of 1 plus cosine of 2 theta. The antiderivative here, well, the antiderivative of 1 would just be my variable, theta in this case. And the antiderivative of cosine of 2 theta, it's almost sine of 2 theta. But if I took the derivative of sine of 2 theta, I'd get an extra 2 because of the chain rule. So I need a 1/2 to kind of cancel out that extra 2. Sine of 2 theta. I guess technically plus c, although that won't end up mattering. Let's distribute the 2 just so I don't have parentheses. I got 2 theta plus sine of 2 theta. I need to evaluate this thing from x values of -2 to 0. Unfortunately, these are no longer x values. So I need to either change these thetas into x's or change these x's into thetas. Let's see, if -2 equals 2 sine of theta, then -1 equals sine of theta, and that happens at theta equals -pi/2. I'll choose that one so that when I plug in zeros for x here, I can just use theta equals 0 because the sine of 0 is 0. I think I'm finally ready to answer this question. All I gotta do is take this expression here, 2 theta plus sine of 2 theta, and evaluate that from -pi/2 to 0. If I plug in 0, I get 0. That's awesome. If I plug in -pi/2, I get 2 times -pi/2, in other words, -pi, plus the sine of -pi, which is just 0. 0 minus -pi gives me pi. Hooray, I'm done. The area underneath this curve from -2 to 2 is the pi that I get from this part plus the 6 that I get from this part. It's the same answer of C. Hallelujah.